Hi, this is Robert Quimby, and I'm going to introduce you to scipy. Now, scipy is a whole ecosystem of different packages and modules, some of which you should be familiar with already. So I'm going to start by introducing you to that ecosystem, and we're going to look at some of the key modules that scipy offers. And then we're going to focus on one module in particular. I'm not going to have time to go through all these different modules. I'll let you explore them on your own. But we'll start with scipy optimize, which is very useful for finding the minimum of a function. So we'll do a basic demonstration of that, and then we'll do something a little bit more advanced using the scipy optimize package. And we'll determine the tilt of the Earth's axis with respect to its orbit around the Sun. So as always, you can get more documentation online if you want to know all the details of this. First thing you should do is you go to scipy.org so you can learn a little bit about this ecosystem, as they call it. And you can see that there's actually a number of different components into scipy. So when people talk about scipy, they could actually mean all of these together. So numpy, which you should have already been introduced to, and matplotlib are considered part of this ecosystem. And so is the actual IPython interpreter. Which if you're using a Jupyter Notebook is basically what you're using as well. There's some other packages that we aren't going to talk about. There's something for doing mathematics, and there's a powerful package, pandas, for working with data structures and doing some data analysis. But what we are going to talk about today is the scipy package itself. So there is a scipy package that you can import into Python, and it has a number of different sub-packages. And you can see some of these listed here in the scipy tutorial. So these are all the different sub-packages here. There's scipy special, integrate, optimize, and interpolate. There's a lot that these offer. So depending on what you want to do, you might want to use one of these different packages. These are some of the ones that I want to highlight for you because these are the ones I find most useful myself. Scipy optimize, which is what we're going to talk about later. This is for finding the minimum of a function, which is a very important thing to do. You can use interpolate when you have, usually if you're given, say, some model data points, some model points, and they're on some grid, so they're not, you don't have all the model points, and you want to find a model point between two model points. You can interpolate that. And there's some other modules for doing convolutions, and if you want to work with matrices and do linear algebra, linalg is a helpful package. There's some statistics in the stats package, and finally there's the integrate package, which allows you to do function integration. And NumPy has some of this functionality actually redundant, so a lot of times you can just import NumPy and you can do a lot of things, like you can integrate in NumPy. You can do some basic linear algebra in NumPy, some basic statistics. But there are some things like optimize where you need to use scipy. So what do you do with scipy optimize? Well, the most basic thing, so optimization, by the way, in this sense, is it's used in the mathematical sense, which means you're trying to find a value that gives you the best, I'm trying to put it in generic terms, maybe best performance. You can think of this as if you have some kind of a cost function, you want to minimize that cost, you find the optimum value that minimizes that cost with the methods and the functions in scipy optimize. So here's what we're going to do. We're going to start by defining a function. All right, I'm just going to call it f, and it's going to take a variable x. All right, so you have to have one variable that you can eventually minimize over. So this is just going to be your generic function. So it's going to return, and we're going to have it return x plus 4 times x plus 1 times x minus 1 times x minus 3. Okay, so you're probably familiar with functions like this. You know what this does. This is just a fourth order polynomial here. And we can actually just see what this is. Maybe it might help to get started. So we're going to import NumPy. as NP, which is often done. Then we're going to set up matplotlib so we can just plot this and see what it looks like. So we'll do our matplotlib magic keyword. We'll do it inline, and then we'll set up matplotlib itself. We'll import matplotlib .pylab pyplot as PLT. Okay, so now that we have that set up, we can, oops, sorry, I needed O there, pyplot. Now we can create some variables and run it through this function and plot it up. So first we're going to just define a bunch of x values. We use numpy linspace for that. And we'll just have values that go from -5 to 5. And let's make 100 of those. Okay. So now we want our y values. We're going to plot x versus y. So our y values are just going to be what this function returns for each of those x values. So we just call f of x, and that's it. So this will call this function, and for each one of these x values, it'll calculate this product, and we'll turn that into y. So now we can plot this. plt.plot x comma y. We'll plot that up, and there's our function. Okay. So what we're going to do now is we're going to use scipy optimize to find the minimum value, which is this value here. You might look at this and you might say, well, I know how to find the roots of that. That's a slightly different problem. So you can easily find the roots, and maybe I'll plot a grid here so you can see this a little more clearly. So of course this function has roots at -4, -1, 1, and 3. But what we want to find is this minimum value here. What is this value where the function gets to its absolute, to its minimum value? Okay. So to do that, let me first start by just plotting this again so we can have this on the same screen. So I'll plot plt.plot x and y again. Start with that. So we have this plot up here. And now what we want to do is find that minimum. So we're going to import a function called fmin. So from scipy optimize, we're going to import fmin. And fmin is a handy function for finding the minima of other functions. So all we do to call this is we just now say fmin, and we give it the name of the function that we defined previously. And that was f. That's just the name of whatever function you've defined. And then you get one more thing, which is the starting guess. Where should we put our initial guess? You can just look on this plot and see it's somewhere around -3, so that might be a good place to start. And we can run this, and if we do that, it'll find that minimum. The minimum value is close to -3, but it's actually -2.935. So it found that value very quickly. It did a number of different integrations. It found that minimum value. The minimum value of the function is -48. So if we call this function f and we give it this value, -2.93, that function f will return this. So this is what that fmin did. It found this minimum value and said the x value that finds that for me is this. So we've now found where this minimum is. All right? So we could have just asked, we can find the minimum value pretty easily. We've already defined y for a bunch of data points, and we can get an approximate value of the minimum just by asking what the minimum of y is, since we have 100 y's. And that's close to what we had before. It's not exactly the same because we just picked kind of roughly spaced values. So when we run this, actually it gives you the proper value here. You can see the exact value, not just our guess value. You might ask, how critical is this value here? Well, we can try different value. We can try 50, for example. And we run that, and boom, we still get the same answer. So there's a lot you can do. You try -50, and you get the same answer. So it's not super critical on getting this, but there is a dangerous spot you may find yourself. What if you said 0 here? Oh, look at that. You got a different answer now. It says it's 2. It's picking this minimum here. So I picked a function here that has 2 minima. So this is the lowest value, but there's a kind of a false minimum here. And if you give it a starting value, a starting guess that's close to this, it might fall into this trap here and get stuck in there. Right, so you got to be careful about what your starting values are. You want to pick something that's reasonably close, because you can see if I pick something that's -3, very quickly it does 12 iterations and it figures out the answer. If I pick -30 and I run, well, it takes more time. It takes 22 iterations. And computers run blazingly fast, so you may not notice it. But if you're doing a more complex function, you may not want to wait for it to minimize. Okay. So, pick a good starting value, the best one you can, and be aware that there could be multiple minima in your function. So you have to be careful about that. Now, there's other functions in scipy optimize besides fmin. This is just kind of the basic one to get you started. Other ones are better at dealing with these double minimum. There's other techniques entirely that you can use for solving such a problem. But this will get you started on minimizing functions. Okay. So if you do want to see some of those other minimization routines, you can look at the documentation for the optimize package, and there is a function called minimize, and there's all kinds of different algorithms you can try out. There's a lot of different methods for minimizing, a lot of different techniques, and it depends on your particular case what's going to work best. Okay, so that's kind of a contrived example. You probably in your career are not going to be optimizing such a simple function as this. You're going to have more complex functions to work with. So I'm going to give you an example that's a little bit more relevant to astronomers. We're going to find the axial tilt of the Earth. So this is the tilt of the Earth's axis with respect to its orbit around the Sun. Right? So first I'm just going to do a little bit of setup here. I'm going to change the default figure size, make it a little bit bigger. I'm going to define a little function here. I'm just going to draw a picture here, and this is going to help me draw that. I'm going to have something draw the axis of the Earth and the equator of the Earth, and I'm going to set up some variables here to do those drawings. So I'm just going to run this cell here, and then here's where we're going to do the actual drawing. So I'll just run this cell so you can see what it does. It makes this plot here, and I'll just describe quickly what it does. So I use this command here to set the aspect ratio to be equal, so that this distance from here to here, that's 0.2, and that same distance is also going to be 0.2 on this axis. Just keeps it nice and rectilinear, so it's not distorted. Then I'm going to plot at 0, 0 a representation of the sun. I'm going to plot a star. I'm going to make that yellow, and I'm going to make it big. Nice big star symbol for the sun. And then I'm going to plot the Earth as a blue circle, and I'm going to make that pretty big as well. And I can put that at the coordinate 1, 0, so it's kind of like you can think of 1 AU maybe, and in the Earth's orbital plane. I'm going to draw a dotted line across here to represent the Earth's orbital plane. I'm going to draw a line here, a thick black line to represent the pole of the Earth's axis, or that's the Earth's axis, I should say. And then I'm going to draw a a dashed line in black to represent the Earth's equator. So that's this line here. Okay, so that's the diagram, and what we're going to ask now is, what is this tilt? What is this angle here between the axis of the Earth and the equator here? The Earth's orbit. Okay. And what we can see from this diagram is I'm drawing kind of a special time. Right? So you as the viewer, you're in the plane of the Earth's orbit. There's the sun over here, and you're looking at you're looking face on to the Earth's pole here, right? And the sun is looking at a special angle here. This is actually during a solstice when this bottom hemisphere here, this lower hemisphere, is having a summer, and this top hemisphere here is having its winter. And what you can see in this case, this angle here, the Earth's tilt, is the same as this angle here, which is the angle of the from the sun to the Earth to this equator line here. And this, if you guys remember, is the declination of the sun. So this is the Earth's equator. This is the line for declination equals 0. And the sun is below that line. So the sun has some negative declination. But this angle here is equal to this angle. And this is something we can use our astronomy tools to measure. So that's what we're going to do. We're going to measure what the angle here is of the sun when it's as far below the Earth's equator as it gets. All right, so you can picture again, if you were the sun, then the declination, you'd be in this equatorial plane right here, so the declination would be 0. All right, so as the Earth goes around the sun, this angle is roughly fixed, and that means the declination of the sun goes up and down and up and down. And when we are at those maxima, or at a minimum, that is giving this angle that corresponds to the tilt of the Earth's axis. So let's do that. All right, so the first thing we want to do is calculate the RA index of the sun over a 1-year period. So we're going to start by importing this time function it's a class from the AstroPy time package. We're also going to use AstroPy units, right? And then we're going to create a bunch of times. So we're going to create array of times that span a year. So we're going to start with today, and then we'll go through 365 days. So we're going to start with now, which is using time.now. That function gives us the current time. And to this, we're going to add an array of numbers. So we're going to get an array. Times is going to be a whole array of times. We're going to use numpy linspace again. We're going to start with 0. We're going to go to 365.25 because that's the number of days in a year. And let's have 100 different data points there. So 100 points evenly spaced between 0 and 365. I need to make these days. So I'm going to multiply by units.day. And now when I do this, let me comment this out for a second. When I do this, we can ask what times is. And it's all these different time objects, right? So we have times at all these different days evenly spaced throughout a 1-year period. Okay? So the next thing we're going to do after we have those is calculate the sun, the position of the sun. And we can use this getTime function from AstroPy coordinates. And you give it this array of times, and it'll give you sun values. And we can look at this. So this is telling us, it's a little hard to see because this is telling us the dates for each one of this, but we have the RA values, for example, for the sun on each one of these 100 data points evenly spread through a 1-year period. And also we have dec, which is what we need here. We need to measure the declination of the sun. Right? So you can see we have kind of a quick way to determine the axis tilt of the Earth. We can, well, let me plot this first, just so we can see what we have here. So we'll plot up the values we just calculated. So I'm going to plot the sun's RA index with red circles. I'm going to label the x-axis right ascension in bold and make the font big. Same for y, but that's the declination axis. And each one of these data points is one of those values for the RA index that we just calculated. And so you can see one way that we can figure out what the axial tilt of the Earth is we just find the minimum and maximum values of this. So the negative minimum value or the maximum value. Let's work on the minimum here. Well, actually, maybe first we can just take the maximum value. And so since we've calculated all these values already, we have those in sun. We can just ask what is the minimum, what's the maximum declination of the sun. So sun.dec.max, and that'll tell you it's about 23.25 degrees. So the actual tilt of the Earth is close to 23.25 degrees, but it's probably not exactly that. And we know this because these are just kind of randomly chosen data points. They don't necessarily include the maximum point, right? There's gaps in between these points, and we have no way to guarantee that we've captured the maximum in here. So one thing we could do is we could go back and we can calculate more of these data points, and then we can just calculate, instead of calculating 100 data points, for example, we could do 1,000 or 1,000,000. Or we could say, well, we know that the maximum value is around here, so we'll just calculate another 100 values around here, and then zoom in and zoom in until we find a value that we're happy with. That's one way to do it, but let's do a different way. We'll do maybe a better way, and we'll use scipy optimize. So we've already done this. We've already imported fmin, so we don't need to import that again. But what we need now is to define a function that calculates the declination of the sun. So we're going to define a function. Let's call this sunDec. And that has to take an argument. We're going to give it an argument dt, which is going to be the delta time, so the change in time from now. So the astropy time is going to be capital time dot now plus whatever dt we had. This is similar to what we did before. Again, multiply this by days, so the astropy understands what we're doing here. And so you can see if I set dt to 1, then this is going to be 1 day from now. Or dt could be 2, and that's 2 days from now. So we've just set some time that's going to be dt days from the current time. All right, so next thing we need to do is calculate the sun position at that time. That's just like we did before. We just do get time or get sun of the time. And then the last thing we need to do is just return the sun declination value. So that's a sun dec. And we'll return it in degrees. Because by default it turns it as an angle, and we're going to just want a floating point number. So we'll return that. Okay, so now we've defined a function that we can call with a number of days from now, and it'll tell us what the sun's declination was at that time. So what we can do is we can find the time that minimizes the sun's declination, and we can use fmin for that. So the let's call this mindec dt, mindec underscore dt. This is going to be the dt that minimizes the declination. That's going to be returned by fmin, and then we have to give it the name of the function we're minimizing. Again, that's sunDec. All right, it was f before, but this time we call it sunDec. And then we have to give it a starting value. Again, this isn't too critical. We can give it 0 maybe to get started, and we can run that, and this will tell us the time value that minimizes the sunDec. But what we want to know is what that sun declination is. So then all we have to do is just run our sunDec function on this value that's returned, the min dec. Okay, so if we run this, we find the minimum declination as that value right there. And this is in degrees. We can actually convert that. So let me save this as a variable. We'll call this mindec. And now we can take mindec and we're going to change it into an angle. So we get that nice degrees, minutes, seconds representation. So to do this, we can use the angle class from astropy coordinates. So from astropy coordinates, we're going to import angle with a capital A. And then we can create an angle from our mindec. We'll just make it negative because this is we found the minimum value, but we care about the absolute value of that, just the amplitude of this sine wave. That's the tilt we care about. So mindec. And this is going to be in units of degrees, so we'll have to tell it. You know, this angle could have been in radians or in degrees or in hours. We're going to tell it it's going to be in degrees, so unit equals units dot deg for degree. And if we run that, here it is in degree form, in degrees, minutes, seconds. So that is the actual tilt of the Earth. And of course, remember as astronomers that we do have this thing called precession. The actual axis of the Earth is slowly moving with time. So if you do this on a different year, this will give you a different value. And we could have supplied a different guess. Maybe we think that the minimum sunDec is going to be 6 months from now. So we can run this again and see again, we get the same answer because it may have taken more time or less time, but it ends up at the same result. All right, so this gives you some idea what you can do with fmin and with the scipy package. But there's, of course, a lot more to do, so explore and have fun.